The global energy landscape in 2026 is defined by a paradox of scarcity amid apparent abundance. Across the developed world, rolling blackouts, deteriorating infrastructure, and skyrocketing utility bills have left the average consumer trapped in an economic chokehold. In the United States alone, the typical household now parts with approximately $150 every single month just to keep the lights on, a baseline cost that has climbed by more than 16% in the last 5 years. As geopolitical fractures redraw the map of global trade and resource nationalism disrupts traditional supply chains, the promise of a seamless transition to green energy has begun to fracture under the weight of its own capital costs. The standard prescription offered by governments and corporate installers is a uniform, high-tech financial commitment. Citizens looking to sever their dependence on an unstable grid, or even just cut their monthly expenses in half, are funneling tens of thousands of dollars into proprietary systems. They are told to buy massive solar arrays, purchase complex lithium-ion battery banks, and tie the entire apparatus together with delicate inverters and specialized charge controllers. A basic residential solar setup with sufficient battery backup now commands a price tag between $15,000 and $30,000 after installation. Yet, from the very moment these systems are activated, an irreversible process of degradation begins. Photovoltaic panels lose roughly 0.5% of their efficiency every year, while expensive lithium cells shed approximately 20% of their total capacity within the first 7 years. To complicate matters further, utility monopolies retain the arbitrary power to alter net metering buyback rates at a whim, a regulatory shift that several states have already executed, effectively erasing the financial calculations that homeowners relied upon to justify their investments. This capital-intensive model represents an intentional structural alignment between corporate manufacturing and the state, designed to prioritize financialized energy solutions over genuine local autonomy. The silent vulnerability of the solar model is laid bare during the winter months, when the sun dips low on the horizon and prolonged weather systems blanket whole regions in gray gloom. A cloudy week in February remains entirely indifferent to a $20,000 solar array. As the lithium batteries drain to critical levels, the illusion of independence vanishes, forcing the consumer to engage backup diesel generators or fall back on the fossil fuel-dependent grid. Meanwhile, an alternative source of kinetic energy remains completely unharvested, whispering through the dark, blowing at night, accelerating during winter storms, and intensifying precisely when residential power demands peak. The mechanical device capable of capturing this ambient power can be constructed from materials found in the plumbing aisle of a local hardware store. For the cost of a single trip and an afternoon spent with a jigsaw, an individual can build a functioning machine that generates usable electricity every single time the wind moves. Yet this option remains completely invisible to the public. It is absent from utility recommendations, ignored by corporate installers, and deliberately excluded from the federal rebate programs that distribute state subsidies. There is a profound geopolitical and structural reason for this enforced invisibility. The modern green energy transition is not merely a technological shift, it is a multi-trillion-dollar race to control the next generation of industrial monopolies. The international supply chain for solar components and lithium-ion storage is heavily bottlenecked by geopolitical rivalries, particularly the dominant manufacturing capabilities of East Asia and the rare earth extraction networks spanning the global south. Western economic policy is deliberately tailored to incentivize capital-intensive, centralized technologies because they can be taxed, financed through corporate banking institutions, and integrated into existing utility systems. A low-cost, decentralized alternative built from raw hardware components presents an existential threat to this financialized framework, offering zero margin for corporate middlemen or state tax collectors. To understand how such a simple mechanism can challenge this global paradigm, one must look at the mechanics of curved plastic interacting with moving air. The core physics behind a polyvinyl chloride wind turbine is older than the modern grid itself, operating on principles that are elegantly simple. When wind encounters a curved surface, it exerts a significantly greater drag force upon the concave side than upon the convex side. This fundamental differential in resistance generates immediate rotational torque. A half-section of common polyvinyl chloride pipe represents a nearly flawless manifestation of this curved geometric ideal. By mounting two or more of these split halves vertically onto a central shaft in a staggered, counter-opposed arrangement, engineers create what is formally designated as a Savonius rotor. As the wind drives directly into the open face of one curved blade, it simultaneously flows smoothly across the rounded, aerodynamic back of the opposing blade. This structural asymmetry produces a continuous net torque that forces the central shaft to rotate. Because the machine operates on a vertical axis, it displays an omnidirectional capability that renders it completely immune to the chaotic wind shifts characteristic of residential areas. Unlike a traditional, commercial horizontal axis propeller turbine, which requires a complex tail fin, an electronic yaw drive, and automated pitch control systems to constantly reorient itself toward the shifting wind, the vertical axis Savonius rotor accepts kinetic input from any angle simultaneously. The design eliminates the mechanical points of failure that plague industrial wind farms, shedding the need for gearboxes, yaw motors, or sophisticated computer controls at the turbine site. While horizontal turbines boast a higher theoretical efficiency on paper, reaching a power coefficient of roughly 40% under ideal aerodynamic conditions, they are severely limited by their high cut-in speeds. A typical residential propeller-style machine requires a sustained breeze of 8 to 10 miles per hour before its blades can overcome inertia and begin rotating. In stark contrast, a Savonius rotor overcomes its static inertia in light, variable backyard breezes as low as 5 miles per hour. While the maximum power coefficient of the Savonius design hovers around 15%, it spends vastly more hours out of the year actually spinning and producing current, frequently outperforming complex horizontal machines when evaluated on an annual cost-per-watt basis. The physical driving force of this rotation is quantified by the stark contrast in drag coefficients across the two sides of the split pipe. The concave face of the plastic blade exhibits a drag coefficient ranging from 1.5 to 1.8, while the smooth convex back yields a coefficient between 0.3 and 0.5. This yields a highly favorable torque ratio of approximately 3 to 1. By expanding the physical diameter of the pipe, a builder increases the total surface area exposed to the wind, thereby amplifying the kinetic torque transferred to the central generator. Splitting an 8-inch diameter polyvinyl chloride pipe lengthwise produces two robust blades, each possessing a chord width of roughly 4 inches, an optimal dimension for generating practical current in a modest 15-mile-per-hour wind. To optimize the power stroke and smooth out the rotational cycle, builders employ a two-stage configuration, stacking two separate sets of blades on the central shaft at a 90-degree offset from one another. This geometric adjustment completely eliminates the aerodynamic dead spot that occurs when a single-stage rotor sits perfectly edge-on to the incoming wind line. Much like a multi-cylinder internal combustion engine where one piston fires while another completes its exhaust stroke, the staggered vertical blades ensure that at least one surface is always catching the wind, preventing the generator from stalling mid-rotation and guaranteeing self-starting capability. The transformation of this mechanical rotation into electrical energy does not require specialized, expensive green tech machinery. The permanent magnet direct current motors found inside discarded consumer treadmills are inherently engineered to act as highly efficient generators when run in reverse. Inside these motors, copper wire coils are wound tightly around an armature that rotates within a static field of powerful permanent magnets. When an external force, such as the spinning shaft of a wind rotor, forces this armature to turn, the copper coils continuously cut through the magnetic flux lines, inducing a direct current voltage proportional to the rotational speed. A standard 260-volt treadmill motor is wound so precisely that it yields approximately 1 volt of direct current for every 25 revolutions per minute of the shaft. When driven by a Savonius rotor turning at 300 revolutions per minute in a moderate backyard breeze, this salvaged motor seamlessly outputs 12 volts of electricity, the precise threshold required to charge a standard deep-cycle battery bank. This eliminates any need for custom-wound copper stators, exotic rare earth magnet arrays, or high-priced industrial alterations. The mechanical connection between the vertical polyvinyl chloride blades and the salvaged motor shaft is entirely direct, bypassing the friction losses, maintenance requirements, and financial expenses associated with belts, chains, or multi-stage transmissions. The power is transmitted cleanly down a simple copper wire, passing through a single blocking diode before entering the battery storage bank. This diode, which can be acquired for less than $2, functions as a one-way electrical valve, allowing current to flow into the battery during high wind events, while preventing the battery from discharging backward through the motor coils during periods of total calm. The historical trajectory of this technology reveals a long-standing tension between decentralized utility and corporate industrial scaling. In the early decades of the 20th century, a Finnish engineer named Sigurd Johannes Savonius recognized that the global march toward complex, centralized electrical generation would leave remote populations vulnerable to economic exclusion. Born in 1884 in Hämeenlinna, Savonius trained as an architect, but devoted his life to practical fluid dynamics. In 1922, he constructed the definitive prototype of his signature vertical axis rotor, mounting the primitive devices onto small watercraft on the lakes of Finland to demonstrate that the simple S-shaped geometry could produce immense torque from unpredictable ambient winds. Recognizing the global utility of his invention, Savonius secured comprehensive patents across Finland, France, Austria, Great Britain, and Denmark by 1926. His definitive 1929 treatise, published under the auspices of the Finnish Academy of Science, meticulously mapped the rotor's performance across a vast spectrum of wind velocities, proving its reliability under adverse conditions. However, the underlying concept predated Savonius by centuries. In 1616, a visionary Venetian bishop and engineer named Fausto Veranzio published a seminal volume entitled Macchinae Novae, which included detailed illustrations of curved-blade vertical windmills designed to grind grain in regions where traditional horizontal mills were unfeasible. The underlying physics had been fully mastered for over 400 years. Yet as the industrial age matured, Western capitals systematically funneled resources into massive horizontal axis turbines and centralized fossil fuel grids. These systems were prioritized not because they were inherently more reliable at a local level, but because their complexity formed a natural barrier to entry, ensuring that energy production remained firmly within the hands of well-capitalized monopolies. The empirical validity of the Savonius architecture is reinforced by its preservation within official state archives and ubiquitous industrial applications. During the height of the 1970s energy crisis, when oil embargoes exposed the structural vulnerabilities of the Western grid, the National Renewable Energy Laboratory conducted exhaustive trials on vertical axis wind machines, concluding that the Savonius configuration represented one of the most durable, low-speed kinetic energy converters ever engineered. Even today, the United States Department of Energy maintains public instructional documents on its educational servers explicitly titled Building the Basic PVC Wind Turbine, intended to demonstrate the fundamental law of conservation of energy to students using cheap, accessible materials. Furthermore, the technology hides in plain sight across every major transportation corridor in the world. The rotating, onion-shaped ventilator caps installed on the roofs of commercial cargo vans, public transit buses, and industrial warehouses are identical iterations of the Savonius rotor. In the 1920s, a prominent German aircraft engineer named Anton Flettner modified Savonius's work to create self-powered extraction fans that rely entirely on the vehicle's forward momentum or ambient breezes to draw stale air out of enclosed compartments. These devices spin flawlessly for decades without a single watt of grid electricity, entirely exposed to highway debris, torrential rains, and sub-zero temperatures, proving the industrial durability of the geometry. The exact same physics that draws heat out of a commercial truck cargo bay can be harnessed to drive electrons into a residential storage battery, requiring only that the spinning vertical shaft be bolted to a permanent magnet motor instead of an air-moving fan blade. The modern re-emergence of this technology has been driven by grassroots builders operating completely outside the bounds of corporate green energy finance. In 2004, an independent couple named Abe and Josie Connolly found themselves living entirely off-grid in the remote, economically marginalized landscapes of rural New Mexico. Confronted by the exorbitant capital costs of commercial solar installations and the absolute absence of utility transmission lines, they began experimenting with salvaged materials to secure their personal survival. Their efforts culminated in the design of the Chespito wind generator, an ultra-low-cost turbine utilizing a blade assembly cut entirely from an 8-inch polyvinyl chloride sewer pipe and a discarded permanent magnet motor pulled from a broken treadmill. For the tail vane, they scavenged the sheet metal casing of an abandoned washing machine, bringing the total out-of-pocket investment for their working prototype to less than $50. In practical operation, the Chespito machine demonstrated a capability to generate 100 watts of clean electrical power in a 30-mile-per-hour wind initiating a steady charge into a 12-volt battery bank at wind speeds as low as 7 to 10 miles per hour. The elegance of the design allowed two individuals, equipped with a basic power drill, a jigsaw, and a standard wrench, to assemble a functional unit in approximately 3 hours. Recognizing the strategic value of energy decentralization, the Connollys chose not to patent their refinement, publishing the complete mechanical blueprints online for free. By 2006, Make magazine detailed the build instructions in its 5th volume, and within 3 years, the open-source design was constructed on national television for the Public Broadcasting Service by John Edgar Park, sparking a global building movement on digital repositories like Instructables. The Connollys eventually expanded their system to a 1,000-watt variant dubbed the Gordo, proving that an array of these low-cost vertical turbines could comfortably sustain the basic electrical needs of an off-grid homestead when paired with a properly engineered battery bank. This decentralized engineering movement is echoed across the globe, cutting through traditional economic barriers and institutional inertia. In Germany, an independent developer successfully built and documented a vertical-axis polyvinyl chloride turbine that utilized a standard bicycle wheel equipped with an internal hub dynamo as its electrical generator. Employing 8 separate half-pipe blades sliced from 4-inch polyvinyl chloride drain pipe, the builder kept total material expenditures under €40. Operating in a sustained 20-mile-per-hour wind, this improvised apparatus yielded approximately 1 watt of continuous electrical energy, providing a steady trickle charge capable of keeping small electronic devices or LED security lighting operational indefinitely without ever drawing from the public grid. Similarly, an organization known as Green Terra Firma advanced the open-source movement by modifying the Chespito framework, pairing a larger 20-amp treadmill motor acquired via online auction for $10 with 3-foot polyvinyl chloride blades mounted onto a heavy-duty dolly-bearing assembly. Under rigorous field testing, this configuration successfully delivered an output of 7 amps into a 12-volt system during a 30-mile-per-hour windstorm, translating to roughly 84 watts of continuous power. This is more than enough energy to keep a deep-sea marine battery perfectly topped off around the clock in any moderately windy locality. None of these innovators held advanced credentials in aerodynamic engineering or electrical sciences. They simply weaponized basic hardware supplies to opt out of a predatory utility relationship. In the developing economies of the Global South, where centralized electrical grids are either non-existent or structurally prone to corruption and collapse, the Savonius architecture has become a vital instrument for rural electrification and economic survival. Communities across sub-Saharan Africa regularly construct large-scale iterations of this technology by slicing discarded steel oil drums in half, welding them to vertical structural shafts, and utilizing the massive torque to drive mechanical water pumps or charge communal cellular devices. The underlying physics remains completely identical to the small-scale polyvinyl chloride variations engineered in Western workshops, substituting specialized polymers for heavy, locally salvaged metals. In the rugged, high-altitude terrain of Nepal, an international aid initiative spearheaded by the organization Practical Action successfully deployed localized Savonius rotors, manufactured from basic sheet metal, to drive agricultural grain grinding mills and power community lighting infrastructure in villages completely isolated from the capital's grid. The total cost per completed unit hovered below $15 in local currency, a sum representing less than the cost of a single month's supply of toxic kerosene for an ordinary lighting lamp. The Savonius rotor succeeds where high-tech Western aid projects routinely fail because it completely bypasses the need for high-precision manufacturing tolerances, clean room component fabrication, or specialized diagnostic tools. If a local community possesses the tools required to cut a basic curve and secure it to a rotating shaft, they possess the means to generate real, immediate electrical energy. The obvious question then arises: if this vertical axis design has been empirically validated for over a century, carries a material cost lower than a single tank of fuel, and can be easily assembled by any individual possessing rudimentary household tools, why does it remain completely absent from the broader consumer market? The barrier is entirely institutional, driven by a complex web of regulatory gatekeeping, municipal zoning codes, and real estate restrictions designed to protect centralized energy cartels. Across the United States, the vast majority of local municipal zoning ordinances enforce a strict residential structure height limitation capped at 35 feet. This height ceiling applies directly to any mast, tower, or energy-generating apparatus anchored within a private yard. For traditional horizontal wind turbines to function with any degree of efficiency, they must be hoisted high into the atmosphere to escape the highly turbulent, low-velocity airflow caused by ground obstruction. At a height of 35 feet or less, an energy harvesting device sits squarely within the chaotic turbulence zone generated by surrounding houses, neighboring structures, mature trees, and perimeter fences. The Department of Energy's official small wind guidebooks explicitly concede that adequate tower height is the single most critical factor determining a turbine's economic viability. Yet local zoning frameworks make it legally impossible for an ordinary citizen to erect an effective mast without obtaining a formal variance. Navigating the variance process introduces an intentionally cost-prohibitive layer of municipal bureaucracy, demanding public hearings, steep filing fees, professional legal representation, and months or even years of administrative delay. The practical impact of this systemic gatekeeping is illustrated by historical precedent. In 2001, a property owner named Bob Lobel applied for and successfully secured a legal building permit to install a small residential wind turbine on his agricultural property in Dover, Massachusetts. However, a mere 3 months into the process, before the mechanical installation could even be finalized, the municipal authority summarily revoked his permit due to organized aesthetic objections raised by affluent neighbors. It required 13 months of grueling administrative hearings and thousands of dollars in personal legal expenditures just to secure the reissuance of his original permit. This case highlights a regulatory framework working precisely as intended, not by passing outright prohibitions on renewable energy production, but by wrapping the process in so much bureaucratic friction and financial risk that the average citizen simply surrenders and continues paying their monthly utility invoice. For those living within master-planned communities, the barriers become even more immediate. Even if a municipal zoning board grants approval for a small backyard wind generator, private homeowners associations hold the legal authority to completely override public statutes. In the vast majority of jurisdictions, the restrictive covenants and deed access codes signed during property acquisition grant these private associations absolute veto power over any external structure visible from adjoining properties or the public street. While a small handful of states have enacted solar access laws to shield consumers from arbitrary association bans, these protections rarely extend real legal teeth to small-scale wind innovations. Even in California, which purports to lead the nation in decentralized green energy legislation, the statutory protections for wind energy are written with massive loopholes, leaving individual homeowners exposed to severe fines and litigation if they attempt to install an unapproved vertical rotor. This regulatory blockade connects directly to the financial architecture of the state-sponsored green transition. The federal investment tax credit, which functions as the primary mechanism making $25,000 solar systems financially palatable to the upper middle class, is structurally restricted to specific classes of certified photovoltaic hardware and commercial wind systems. A home-brewed polyvinyl chloride wind turbine is entirely excluded from these financial incentives. This exclusion has nothing to do with the machine's capacity to generate electrons, which it does reliably, but because it cannot meet the rigid institutional definitions deliberately written into the tax code by industrial lobbyists. The entire Western subsidy apparatus was engineered from its inception to support corporate manufacturing lines, creating an ecosystem where alternative, zero-capital solutions are rendered structurally invisible. No commercial green energy contractor will ever recommend an elegant $20 vertical axis turbine when their entire business model and sales commission depend on financing a $30,000 residential solar array. No public utility rebate registry will ever validate a decentralized generator constructed in a private garage out of salvaged hardware. No real estate appraiser will ever factor an ordinary piece of plumbing pipe and a used treadmill motor into the baseline equity value of a suburban home. The institutional structure is not ignoring this technology because it fails. It is actively marginalizing it because there is absolutely no opportunity for corporate capital extraction. This financial exclusion goes far deeper than federal tax codes, embedding itself within the insurance and banking systems that underwrite modern property ownership. The Small Wind Certification Council serves as the primary regulatory gatekeeper for the small-scale wind sector, mandating that any turbine seeking commercial deployment must undergo thousands of dollars worth of standardized laboratory testing to receive formal certification. Because no independent tinkerer or local hardware store is going to invest hundreds of thousands of dollars to certify an open-source design made from basic PVC sewer pipe, the technology remains perpetually uncertified. Consequently, no licensed, bonded electrical contractor will touch the installation. No commercial banking institution will issue a home improvement loan to finance it, and no major insurance provider will cover the property under a standard homeowners policy if an uncertified kinetic device is found anchored to the land. The Distributed Wind Energy Association openly identified these hyper-localized zoning hurdles and certification costs as the single greatest barrier preventing the widespread adoption of small-scale wind tech across the United States. A comprehensive study compiled by the National Renewable Energy Laboratory confirmed that up to 50% of all individual applicants seeking permits for small wind installations in various states were either explicitly denied by local boards or chose to abandon their projects entirely after encountering insurmountable cost overruns and bureaucratic delays. This is not an engineering failure. It is a manifestation of institutional gatekeeping masquerading as a concern for public safety. For those determined to break through this corporate perimeter, the physical assembly of a functional Savonius generator requires only a small bill of materials and a clear understanding of basic fabrication. The construction sequence begins with a standard length of 8-inch diameter polyvinyl chloride pipe. It is vital to procure Schedule 40 sewer pipe, as this specific grade offers the necessary wall thickness and structural rigidity required to withstand intense centrifugal forces and mechanical loads during high wind events. A simple 2-foot section of this material can be purchased at any standard hardware outlet for approximately $4 to $6. Utilizing a basic measuring tape, the builder marks the exact center line across the entire length of the cylinder before using a common jigsaw or reciprocating saw to split the pipe cleanly into 2 symmetrical halves. These 2 semicircular troughs form the aerodynamic blades of the wind rotor. Sourcing the electrical generator requires a brief excursion into the secondary consumer market to locate a permanent magnet direct current motor, ideally one salvaged from an industrial or residential treadmill. The premier specification for this application is a motor rated at 260 volts of direct current, with a continuous duty threshold of 5 amps. Pre-equipped with a robust 6-inch threaded hub assembly. These motors are incredibly common, regularly found at neighborhood garage sales, scrap yards, or online secondary marketplaces for prices ranging between $10 and $30. If a treadmill motor is unavailable, any permanent magnet motor that demonstrates an output ratio of at least 1 volt for every 25 revolutions per minute will serve perfectly. The structural frame that holds the assembly together is fabricated from approximately 36 inches of 1-inch square steel tubing, paired with a standard 2-inch floor flange, a 2-inch by 4-inch threaded pipe nipple, and a small assortment of heavy-duty self-tapping screws. The directional tracking mechanism requires a simple tail vane possessing roughly 1 square foot of surface area, which can be easily sliced from the lightweight sheet metal paneling of a scrapped washing machine or household dryer casing. To safeguard the electrical circuit, the builder must integrate a 30 to 50 amp blocking diode into the output wiring, which effectively prevents the battery storage system from discharging its energy back through the motor coils when the wind falls below the charging threshold. Assuming every single component is acquired brand new from commercial retail shelves, the complete capital investment required to build this functional generator hovers between $15 and $30. If an individual leverages basic scavenging strategies to source the motor and sheet metal from local waste streams, the total cash expenditure drops below $10. The necessary toolkit is limited to standard household implements: a jigsaw for slicing the polymer pipe, a power drill equipped with a 7/32 drill bit, a 1/4 inch by 20 tap to thread the mounting holes directly into the motor hub, a standard wrench, wire strippers, and a basic manual screwdriver. The entire assembly process requires absolutely no welding or specialized metallurgy, though a welded frame will naturally offer enhanced durability over decades of exposure to extreme weather. For a novice builder embarking on their first build, the total assembly time ranges between 4 and 6 hours, while 2 experienced individuals working in tandem can easily complete a unit within 3 hours. However, operating a decentralized kinetic energy system requires strict adherence to specific material realities to prevent premature mechanical failure. Polyvinyl chloride polymers are highly susceptible to chemical degradation when exposed to continuous solar ultraviolet radiation. If the raw white plastic blades are left entirely unprotected, they will become intensely brittle and prone to structural fracturing within 12 to 24 months of continuous outdoor exposure. To mitigate this vulnerability, the builder must apply a protective barrier using any standard exterior latex paint. Applying 2 thorough coats of ordinary latex paint, a modification costing less than $5, makes the difference between a rotor that shatters after a single season and an asset that continues generating power for over a decade. For the supporting tower infrastructure, a 10-foot length of 1 1/2 inch galvanized steel water pipe anchored securely into a solid concrete footing provides a robust, resilient mounting platform for a backyard installation. To ensure structural stability during severe windstorms, high-tensile guy wires should be integrated at every 18 feet of vertical tower height, anchored out into the ground at a distance equivalent to at least half the total height of the mast. Elevating the turbine assembly higher into the local slipstream is critical. Lifting the rotor even 10 feet above the immediate roofline of surrounding structures dramatically reduces ground-level turbulence, providing a cleaner, faster airflow that translates directly into exponentially higher electrical output. The storage architecture required to capture these captured electrons begins with a single deep-cycle marine battery possessing a capacity rating of 100 amp-hours. A component readily available at any regional automotive supply outlet for a price between $80 and $120. This chemical storage unit must be paired with a basic charge controller configured to match the specific voltage parameters of the residential system. A standard 12-volt pulse width modulation charge controller can be easily sourced through online marketplaces for an investment of $15 to $25. For those seeking comprehensive, step-by-step mechanical schematics, parts sourcing indices, and detailed tower construction blueprints, the open-source website, maintained by Abe and Josie Connolly under the domain velacreations.com, provides complete documentation entirely free of charge. Furthermore, the United States Department of Energy continues to host free, open-access instructional guides for constructing a basic vertical polymer wind turbine on its energy efficiency and renewable energy educational subservers, providing a blueprint that is perfectly scalable for any residential backyard workspace. However, any objective strategic analysis of this technology must also confront its inherent limitations before breaking ground. A single 100-watt DIY vertical turbine is not a magical energy silver bullet capable of instantly disconnecting a modern, high-consumption household from the commercial utility network. It is designed to act as a resilient, low-cost supplement to an existing power strategy. To achieve total, non-grid energy independence, A homeowner must deploy either a distributed matrix of multiple vertical turbines or construct a diversified hybrid network that deliberately couples wind generation with a traditional solar array. Furthermore, wind energy remains entirely dependent on geographic topography and localized microclimates. If a residential property is densely hemmed in by multi-story commercial buildings, dense urban structures, or thick canopies of old-growth trees without any clear clearance above the roofline, the incoming wind will be rendered highly turbulent and mechanically weak, resulting in low electrical yields. Because of these structural realities, the Department of Energy explicitly discourages homeowners from mounting kinetic wind turbines directly onto the physical framework of residential roofs, as the continuous mechanical rotation can introduce unwanted vibrations, acoustic noise, and sustained structural stress into domestic load-bearing beams. Safety considerations must also be prioritized during high-velocity wind events. When spinning at maximum revolutions per minute, a home-brewed polyvinyl chloride blade assembly carries immense kinetic energy. A catastrophic structural failure at full speed can transform the polymer into sharp plastic shrapnel moving outward in every direction. A builder must never stand directly downwind of an active, unbraked turbine and should always short-circuit the motor leads or dump the output into a dedicated electrical load whenever performing physical maintenance near the rotating blades. Finally, it must be understood that this home-built system is fundamentally a 12-volt direct current apparatus engineered to charge chemical battery banks. It cannot directly run a standard kitchen refrigerator, a central HVAC compressor, or a household washing machine without modification. Converting this stored direct current into standard alternating current requires the addition of a pure sine wave power inverter. A high-quality inverter rated for a continuous load of 1,000 watts can be acquired for approximately $100 to $150, an investment that represents a mere fraction of the cost of a commercial solar package, but one that must be factored into the economic calculus of the project. When the global energy paradigm is stripped of its corporate marketing spin, the choice confronting the modern consumer is remarkably stark. A fully functional vertical-axis Savonius wind turbine can be fabricated for less than $20 in raw hardware materials, while a standard utility-scale residential solar grid with comprehensive battery backup commands an upfront capital commitment between $15,000 and $30,000. The simple vertical turbine initiates electrical generation in a gentle 7-mile-per-hour breeze, while the most advanced photovoltaic arrays on Earth stop producing energy the moment the sun slips below the horizon. The underlying physics of the Savonius rotor has been field-tested and proven across global shipping corridors, logistics networks, and isolated communities for over a century. Conversely, the high-priced lithium battery banks sold by corporate installers are guaranteed to shed up to a fifth of their total energy capacity before a child completes their primary education. The corporate solar model is backed by a multi-billion-dollar lobbying apparatus, institutional tax credits, and an army of certified sales representatives. The low-cost vertical turbine relies on a split section of plumbing pipe, a salvaged motor, and an open-source instructional manual. Yet, despite the complete absence of institutional backing, the vertical rotor represents a system that any citizen can construct over a single weekend in their own backyard for less than the cost of a standard family meal. You do not require an official municipal permit to erect a microgeneration mast under 35 feet in the vast majority of legal jurisdictions. You do not need to compensate a licensed industrial electrician to wire a low-voltage 12-volt battery bank, and you absolutely do not require permission from a corporate board to cut a piece of plastic pipe in half and bolt it to a salvaged treadmill motor. The engineering data is free, the raw materials are universally accessible, and the only barrier standing between an individual and a state of personal energy resilience is a simple trip to the local hardware store and an afternoon spent working in a garage.